Hello, this is Dr. Muhammad, and this is another video under Dynamics of Structures course. Today we're going to talk about forced vibration, response to arbitrary general dynamic loading, and this is going to be part 1. Okay, and today we are going to talk about first of all, I'm going to talk about the response to unit impulse, because this is an important concept that we need to understand and go through it very well so that we can use it for obtaining the response of arbitrary general loading. So first of all, we need to understand what is the meaning of the unit impulse and what is or why we are going to study it or to understand this concept before going and indulging into the arbitrary general arbitrary loading. So first of all, we need to make a definition for this unit impulse, which is it is like a very large force that acts for a very short time, but with a time integral that is finite, and this is what we call the impulsive force. Okay, so let's use this. So here it's the key words here are the very short time, this is number one, okay, and very large force. So if we have these two things, then we are going to have what we call it the impulsive force, as you can see it here. So you're going to find, if we have a relation between tau, which is the time domain, the time elapsed, and we are having in the vertical axis the f of tau, which is the force being applied or the arbitrary force. This is the arbitrary force. As you can see, it is a generic or general loading, and we are going to look to this general loading based on these slices that you can see here. We're going to take a slice of this loading along this time axis, and we are going to call it d tau, which means that a very small amount of time. And based on this, we're going to find that this force is going to be, or at least we are having one rectangular, as you can see here, its height is the force at this specific point, and its width is the time domain that we are talking about. It's a very short time. Okay, so this is what we call it the input impulse or response to input impulse, which means that we have generic loading, and we are going to look to one part of it or one small slice of it, and we are going to focus on it as it is individual pulse loading or individual force, and look how we can obtain the response after that. Okay, so why we need to study the impulse loading? Because real structures are subjected to loads that are not harmonic, as we studied before. Because generally speaking, all the structures that we are going to find and we are going to encounter, they are not having, or they are not exposed to simple harmonic motion, as we have explained before. So this is actually not the case. Not all structures, they are having like this exposed to simple harmonic motion, where the force can be described by sinusoidal function, whether it is sine or cosine. But actually the type of loading that we are going to find or that we are going to encounter for any type of building is generic loading like this. So the point is, we are going to after understanding this impulsive force and how we are going to obtain the response for it, then we are going to understand how we can integrate the entire domain in order to obtain the response for the generic loading. We will study the response of single degree freedom system to general loading using the concept of impulse loading as I have mentioned here. Okay. We shall see that this concept will help us to obtain the force using an integral that can be solved analytically if the force function is simple. So that's the point actually here, that we are going to, let me check something here. So we are going to find that for this this concept is going to help us to obtain the response using an integral that can be solved analytically if the forcing function is simple. This is one key concept that we want to understand, that if our function, the forcing function, is simple. Simple means that we are having like triangular loading, for example, or if we have rectangular loading, something like this, the relation between t and f of t, this is considered to be a simple loading that we can understand well, and we can put some equations and we can put it into the solution in order to obtain closed form solution for the response of the structure. However, if the forcing function is complicated, for example, if we're talking about earthquake loading, commonly earthquake loading is going to be something like this, right? It is generic. It is something that we cannot control, and we are not having like a simple form for this earthquake or for this type of function. In this case, we are going to use numerical integration procedure in order to get the solution. Okay, so the concept, as I said before, we need to understand that whatever that we are doing now is related to like looking to the force and trying to take slice of it, as we have said here, and then we are going to look to this slice as if it is impulse loading, and we are going to see how we can use this concept, which is impulse loading, in order to get the response of the structure. Then we are going to integrate, we are going to use different impulses for this period of time that is the load is being applied, and we are going to superimpose the responses coming from these impulses. Okay, so this is what we are going to follow. Okay, last thing, it is only the definition that I have said before. An impulse, an impulsive loading is the load which is applied during short duration. So the point is we are talking about something that is very short duration, something like this, for example. Okay, this is what we call it delta tau, or we call it d tau, okay, of time. The corresponding impulse of this type of loading is defined as, so the impulse is going to be defined here. The impulse is going to be the area of this curve that we are talking. If we are having f of t here, for example, and here I cannot write here actually, here t, so we are going to have this area is going to be the impulse for this type of loading. So it is defined as the product of the force and the time of its duration, okay, which we call it the area under the curve, the area under the curve, okay, and we show it before as I have shown it here. This is the area under the curve is considered to be the impulse force. Okay, now let's go to the next part, which is general dynamic loading. We are going to look to it and see how we are going to deal with it. Okay. Okay. So now let's go and understand a little bit more about the point that we were discussing. First of all, the arbitrary response to arbitrary general dynamic loading, as we said, it is going to be based on this concept of impulsive forcing, which is, as we have defined last time or in the last page, it is f of t times d of tau. Actually here t or tau, they are not a big deal now if we are dealing with the force itself, because it is time, okay? So here it is supposedly to be like f of t or f of tau. They are going to be like synonyms here, but later on I'm going to make or give differentiation between tau and t, okay? So anyway, this is considered as tau now, okay? F of tau and times d of tau, as we are having the horizontal axis to be the time and the vertical axis is going to be the force itself. Okay, so the concept is, as I said, we will use the concept of impulse loading to evaluate the response of the linear. So this is one key word that we need to keep in our mind. Linear. We are talking about linear system, not nonlinear. It's very important, okay? Because we are going to make superposition. Generally, whenever that we are having superposition or whenever that we have linear system, we can superimpose their responses. But if these systems are nonlinear, then this means that we cannot use superposition in general, okay? So in our generic dynamic or arbitrary general dynamic loading, one of the key concepts that we are going to use the impulse force, and we are going to like give different or divide this loading into different slices. As you can see, each slice is going to, or we are going to calculate the response of the system for each slice, and then we're going to superimpose. One major concept here or assumption that the system is linear. Our system is linear. Okay, and another key also that we are going to assume that the system, it is at rest, means that V node equal U node equal to 0. U node equal V node equal to 0. Okay? Okay, now let's go to Then by adding the response due to the infinitesimal pulses, we can get the total responses by superposition, as we have said. So superposition is going to be used, or we are going to use it as we said. Okay, infinitesimal pulses going to be added together. Okay, now let's go to the next part, which is related to the understanding how we can find an approach for the solution. First of all, we're going to start with Newton's second law, okay? And in this law, we are going to give the definition based on which we usually like derive the equation. The change in momentum equals to the net force applied on the mass m, or this object m. Okay, so this means that we are having here the m times delta v over delta t, where m, it is the mass of the system, delta v, it is the change in the velocity, and delta tau, it is the change in time. Okay, so this would equal to, this is the change in momentum, right? The change in momentum, as we said here. This would equal to the net force applied on the mass m. So the left hand side, which is the change of the momentum or change in momentum, equals to the right hand side, which is the net force applied. Okay, looking to the right hand side and left hand side, we're going to rearrange it, and we are going to put delta v equals to f of tau, which is the force applied over the mass, times the infinitesimal time tau, which is d tau. Okay, so keep this in your mind now. So now we are going to say that the change in velocity between, if we have an impulse, something like this, for example, okay, so the change of the velocity from this point to this point, okay, which is going to be delta v, we can define it based on the infinitesimal d tau, the time, and in the same time we can define it using the force itself, which is F of tau, and the mass of the system. These are the three main components based on which we can define delta V. You're going to ask me why we are concerned with the delta V. You're going to see in a minute why we are concerned with the delta V. Okay? Because everything actually on the right hand side is known for us. F of t, it is going to be known for us. The arbitrary loading, we are going to have the function, whether it is simple function or complicated, we know it. And m, it is the mass. Usually it's a given. And delta tau, it is the variable which is based on time. And the only thing that we want to know now is delta v, which is the change in velocity from this point to this point. Okay, now let's have some notes here, important notes on what we have discussed up till now. Okay, first of all, since the force is applied in a very short time, the elastic forces can be neglected, and the response after termination of the loading is free vibration. Okay, what is the meaning of this? Let's read it carefully, step by step. Since the force is applied in a very short time, we agree on this. Our force is applied in a very short time. So this is considered to be the condition that we are going to talk about. Okay. So the elastic forces can be neglected. The elastic forces, what is the meaning of elastic forces? Exactly, it is K times U. The stiffness of the system times the displacement should equal to 0. Really? Yes, that's right. Because during very short time, okay, during very short time, the system couldn't have this enough amount of time in order to develop the elastic response, okay, or the elastic forces. We need stiffness to be like the elastic forces to be developed in the system. We are talking about very small amount of time, infinitesimal d tau. This means that we are talking about small amount of time that would not provide the enough time for the elastic forces to be developed. So now there is something that we are going to have here, which is important thing for us, that one part of the equation of motion for this impulse force is going to be like, we know it's going to be 0. Okay, it can be neglected here. Okay, why I put it here as a note? Because the elastic forces need some time to be developed. That's the main, or the key, we can say the main cause, the root cause of this. And the response after termination of loading is free vibration. What is the meaning after termination of the loading? Here, this is the termination of the loading. It is going to be, the response is going to be something like this. Okay, here, this response is free vibration. Okay, so this is another key concept, that after the impulse finishes, we are going to find the system is responding in a free vibration response. Okay, is going to have free vibration response. Okay, so this is first note about what we have explained before about the impulse loading. Remember that we are talking about impulse loading and impulse response on the system. Okay, okay, that's very nice up till now, and let's go to the next part, or the next note for us. The damping. Okay, the damping. So remember here, K times U equal to 0. Now, the second note is the damping will not be considered. What is the meaning of damping? C dot U node equal to 0 also. Because duration of the pulse is very short, so the energy will not be absorbed by damping. This is another issue that we need to consider. The system will not be able, because also the short time that we were talking about, okay, if this is U of t, for example, and this is tau or t, whatever now, okay, if we're going to find that this is the force, or this is the impulse, okay, And then we are going to find that there is no enough time for the system to absorb, or the duration is very small. Okay, so the energy will not be absorbed by damping. The energy that is going to be accumulated during this very short time is not going to be absorbed by damping. Okay, do you remember the sources of damping that we have explained before? We have different sources of damping, structural damping, that we have like different parts that is going to be responsible to the damping, or the considered to be main sources of damping during the excitation. In this case, this small duration would not allow energy to be absorbed by damping. So we have another thing here, another key for us, Cu dot equal to 0. This is a second hint that is important. Elastic forces in note number 1 was 0, and then we're going to have damping forces is going to be, or damping forces are going to be 0 as well, okay, because the energy will not be absorbed by damping due to the duration, the short duration. And the third note, also since the load is applied in a very short time, you can see that the word very short time or duration, okay, very short time here also, this means that there is something special for the impulse loading that is different than others. So we're going to find elastic forces are 0 and the damping forces as well. Okay. Then we're going to find that since loading is applied in a very short time, the response of the system can be described by the undamped free vibration equation. That's right, because we are going to deal with system that is undamped, because damping is not going to be developed. Okay, so our system is going to be undamped free vibration, and the equation that we have developed before can be used for this purpose, okay. Okay, so this is the main things regarding this issue. So let's now go to the next slide. Okay, so we are going to talk about this note, which is note number 4. Okay, sorry for this. Okay, we're going to use this. Since the duration of pulse is short, again, the same cause that we are repeating it, okay, the initial velocity can be assumed equal to the increment and the velocity. Okay, we are going to use, or we are going to claim that in this case, the initial velocity, which is one of the important keys for understanding the response of pulse, impulsive force, that the initial velocity that is going to be here at the beginning can be assumed equal to the increment in the velocity. What is the meaning of this point? Let me light here. Okay. If we are going to have the relation, as you can see here, between tau and f of tau, which is the force and the time elapsed for this force, and we assume that we have the pulse to be like this huge amount of force in a very short duration. As you can see here, we are having this pulse started here at this point and ended at this point. The difference between the two, we call it d tau, which is the duration of the pulse, and the start of this pulse starts after tau time. Okay, so starting from this point to this point, we were starting from v, which is the velocity here, and the displacement were 0. Both of them were 0. Why? Because the initial conditions here, it is at rest, okay, at rest initial condition. Based on that, we are going to find that The initial conditions here, u node and v node, or v at time tau, is going to be 0. And then after d tau, we are going to find that the velocity and displacement is going to be given, as you can see here, which is u node equal to 0, because it is going to be the same displacement. The system will not react or will not give us anything or will not displace during this short time. So at this point also, we are going to find that our system is having u node equal to 0 and v at tau plus d tau equal to delta v. Okay, delta v. Okay, so based on this, we are going to find that the increment that took place in velocity between this point, which is at time t, or tau, sorry, and at time tau plus d tau, the increment in velocity is going to be, or the increment is going to be the initial velocity for the remaining part of the free vibration for the system, right? Because this is considered to be the initial condition for the system or our system when it starts its free vibration. We said before that we have impulse. This impulse is going to give shock to the mass, and at the beginning of the impulse we have at-rest conditions, which means that u node equal to 0 and v node or v tau equal to 0. After a short duration of d tau, the velocity is going to greatly change from v equal to 0 to v equal to delta v, because we have a great momentum is ready input to the system. So we are going to find that the velocity is going to change from v equal to 0 to v equal to delta v, which is the change in velocity till this point. And u is going to be, or the displacement, the system did not respond yet because it's very short time. The system couldn't respond. Okay, so based on that, we are going to find at this point we have the initial condition to be u node equal to 0 and v, which is the velocity, is going to be which is v at time equal tau plus d tau equal to delta v. Okay, well, if we want to obtain the response of the system at any arbitrary point at time t, okay, on the horizontal axis, so this point t, if we're going to give how much exactly the time between this point and this point, which is the end of the impulse and the start of the real free vibration of the system, this distance is going to be t minus, between parentheses, tau plus d tau, right? So this is d tau and this is tau, as we indicated here, right? Okay, so based on that, we are going to claim that d tau is very small, infinitesimal, right? Infinitesimal slice, which is going to be, we can neglect it, we can say that this is 0. And based on that, we can claim that this distance equal to t minus tau, right? Okay, at this t, which is at any point on the time axis, at any point of the time axis. Okay. Okay, based on this, our initial condition at this particular point, as I've said before, is going to be, yes, v node, which equals to delta v, as we said before. The initial condition here, v equal to delta v. V here was 0, v here equal to delta v. The change in velocity was huge. Okay, so the initial condition here at the start of the free response is going to be delta v. If you recall the last or the previous slide, I mentioned about that delta v is going to equal f of tau times d tau over m, right? From the second law or Newton's second law. right? And we have u node equals to 0. This is something that we know, right? So based on that, we are going to have our initial condition for our system, okay, to solve it now. So we have, this is a free vibration. Remember, Will, that we are talking about free vibration. We're talking about free vibration because the system here, the system here is going to be under free vibration. Okay. Okay, now let's go here. Now, note number 5 regarding the pulse excitation, we're going to find that the solution of the equation of motion, okay, as for the undamped free vibration, it is going to be similar to the case of the undamped free vibration, which already we have explained before. We have initial conditions, we know them, U node and V node, and we know the equation, which already we have explained in the previous videos. So we have U of t, which is the total response, equals to U node times cosine omega t plus V node over omega sine omega t. From where we got this equation, please visit maybe the second or third video and you are going to understand exactly from where we got this video. Already we have derived it before based on the equation of motion for a single degree of freedom system. Okay. Again, you are going to find that the parameter of time that we are using is t, right? In the common equation. But as I have mentioned before, it is going to be t minus tau plus delta tau, right? So we are going to neglect this delta tau because it's very small. So we can say that it equals to 0. Then our variable of time, or the time variable, is going to be t minus tau. T minus tau. Okay, it is the time elapsed. Okay, and tau, it is a constant of time. That is how much the response, or how much our system was at rest or in the previous condition before the start of the impulse. That's the meaning here. So we are going to change this variable t, and instead of t we are going to put it t minus tau, as you can see here. Also here we're going to put it t minus tau. That's it. Okay, from this concept. And then we are going to know, we're going to put u node. We found that u node, already we've mentioned about this, u node equal to 0. The initial condition equal to, or the displacement equal to 0 at this initial, the initial condition, the u node equal to 0. So we are going to find that our equation is this term, which is the first term, is going to be cancelled because u node equal to 0. So the second term is going to remain with us, v node over omega, sine omega t minus tau. Well, we are going to take this term and put v node here, and remember that we have already mentioned about v node here. V node equal to delta v, which is already we have obtained it from the definition of the impulsive force and from Newton's second law. So we are going to end up with u of t equals to f of tau, the force that is being applied, times the d tau, which is the time parameter, over m, the mass of the system, over omega, which is the natural frequency of the system, sine omega t minus tau. Omega t minus tau. This is what we call it the solution for one pulse only. If we have one pulse, then we are going to have this solution. We are going to have this solution. Okay, is it clear? I hope that everything is clear with you. Okay, now let's go to the second or the next part, which is note number 6. Remember, these notes that I'm talking about here, they are like understanding or giving important hints about the impulse loading in general. So try to understand them very well, because they are going to adjust to you everything regarding our impulse loading, and then we're going to understand easily. You're going to find at the end the generic loading or the response to generic loading is very easy after understanding the impulse loading. If we have more than one impulse, okay, now we are going through, or we are going toward solution of the generic loading. If we have more than one impulse between tau equal to 0 and tau equal to t, okay, then with at-rest condition, this is another condition, means that u node equal to v node equal to 0, and for undamped system, then we are going to solve the previous equation in the previous slide. We're going to solve it with putting the integration, this sign of integration, from 0 to t. So the previous equation, if you revisit the previous equation, it was f of tau over m times omega times sine omega t minus tau times d tau, right? Just we added something here, which is the integration part, and we put it limited integration, because really we have limited integration here. Okay, so we have, like, if we go back, so if you look here, yes, if we are going to have different or another types, if we're going to have another types of the system or impulses here, we are going to find that we need to have like integration of whatever that we have from these slices, which is the pulses, right? Okay. Okay, and after that we have mentioned about this is the equation that we had. This is our response. This is the response of the system, and we have f of tau times d tau over m times omega sine omega t minus tau. Then if we are going to use, or if we are going to have the different number of slices, then we are going to put here the integration sign, and we are going to put it limited from 0 to tau, and then we are going to take this m and omega outside of the integration and put f of tau, okay, times d tau. We can put this like at the side, and then sine omega t minus tau, okay, t minus tau, which is this one. Okay, so this is actually what we are going to like give it a name. Okay, in the next slide we're going to give it a name, which is Duhamel integral. So let's remove this. Okay, this is our equation, as you can see here. Okay, the integration for many responses from many pulses. That's right, and it is going to be, the force is going to be one important like factor or ingredient in this equation. And then we are going to have the sinusoidal function, which is going to contain omega, which is the natural frequency of the system, and t minus tau, which is related to the time, and d tau, which is the time parameter. Okay, this equation includes both steady and transient states for at-rest initial condition. So this equation, because if you remember from the previous videos, we were talking about steady state and transient state. So in this case, we are talking about something we cannot see where exactly transient and steady, but it is, this equation is describing both for us. It is describing both for us. Okay. So now this equation, which is having this integral, we are going to call it Duhamel's integral for undamped system. Duhamel's integral for undamped system. And remember that it is for initial condition equal to 0. I mean that u node equal to v node equal to 0. Okay. Now we understand everything for this equation. We understand from where it came. We understand why we put this integration. We understand what is the meaning of 0 to t, because any other pulses, as I'm going to show shortly, within the domain of the force or within the if we have from 0 to t number of pulses, which is going to be described by the force, then we need to integrate them. The sine means that we are having sinusoidal function. Our response is going to be sine in a sine form. And omega means that the natural frequency of the system is going to take or play a role in the response, as we can see also from the outside of the integration here. It is outside of the integration means that it is considered to be a constant, and in the same time it is inside the sinusoidal function, means that it has a role in the response of the system. Mass is always there, and then we are having, this is considered to be two parts in itself, transient and steady. Okay, transient and steady. Okay, so we call this Duhamel's integral. Duhamel's integral. Okay, now let's go and let's understand more about it, and let's understand the meaning of the graphical representation of Duhamel's integral. I think I need to make it a little bit smaller so that we can see better. I think this would be better, I guess. Okay. Okay, so in this case we are going to have I'm going to draw, as you can see here, I have drawn the relation between u of t, which is the system response, versus t, which is the time elapsed on the time axis of the system, and not perpendicular, but just it is making or crossing it another system or another axis, which is tau with f of tau. So the vertical axis here, it is u of t, which means that the system response. And the horizontal axis, which is the black one here, it is t, which is the time elapsed on the horizontal axis of the system response. And there is a crossing line here, which is going to be another line called tau. This tau is going to be also time, but it gives to us, or it measures the time elapsed by the force or the generic force. So as you can see here, this line is like the wavy line here. It is giving to us the generic loading of this force. Okay, it starts from 0. And the vertical axis is going to be the force itself, the function of the force itself. Okay? Okay. This pulse, as you can see, it started after time on the tau axis called tau. Okay? It's like fixed time, for example, here. And also we are going to say that our system was at rest for a time tau, and all of a sudden it was excited by one impulse coming from this force, or coming from this generic force function, as we can see. At the end of the impulse from this generic loading, then we're going to find that our system is going to respond in this blue line, as you can see it here. This is the system response, the free response of the system. Then at any arbitrary point along this axis, which is t, at point on this axis, which is t, as I said, this distance, which is the time that is going to be responding, or the system is going to respond freely, we're going to find that this portion on the axis is going to equal t minus tau. T, which is this time, all of this is t, and then minus tau, which is this amount of time before the impulse is exciting or being triggered or exciting the system. Okay? Okay. So this, as I said, it is the system response with the black axis. The red axes, they are the force function, or they are representing the force function. Okay. Now let's go to the next understanding, to understand how we are going to give the definition for our system, still we want to understand how our system is going to be defined if we have different slices, as you can see here. Okay, so first of all, if we are going to have our system, as you can see in black, represented by the black axes, and we have the red axes, we're going to say that maybe the force is going to like stay on the system for a specific amount of time. This specific amount of time is going to be like divided into slices. From here it came the impulse loading concept. We are going to divide this portion of time into 5 slices, 5 pulses, as you can see here. And we are going to say that each pulse of these pulses is going to respond, the system is going to respond to it using the equation that we have explained, which is Duhamel's integral. Do you remember? Then we are going to have for example, for pulse number 1, okay, for pulse number 1, for example, we are going to have this this response of the system, which is at the end of pulse number 1. Okay, so this is 1, for example. And then at the end of pulse number 2, we are going to find that this is the response of the system for pulse number 2. And here this is number 3. Okay, and here it is number 4, and here number 5. We are going to have at the end of each pulse the response of the system. But these pulses and these responses, they are individual. We are going to sum them up. We are going to sum them up. Okay, so each one of them is going to provide for us like part of the total response of the system. So this means that we are going to sum them up, okay, in order to get the total response of the system. So starting from here, for example, we're going to say that how the system is going to, we're going to add all of these responses together, okay. Then at the end we're going to have the total response of the system. Like superposition, using superposition, we're going to have the total response of the system, as you can see, okay, u of t. Every one of this we call it du, part of the total response. However, this system here, it is going to be u of t, which is the total response. Okay, so this is the system response to individual pulses, we denote it by du. And here it is the total response of the system due to all pulses together. All pulses together, they are going to be responded, or they are going to be here. Okay. Okay. Okay, so this is known, which is the superposition of all the forces or the responses together. If we have this is the force versus the time tau of the force, and we are going to divide the force to slices, more slices, as you can see. Every one has width of tau and width of d tau, and at any particular point after tau time, then every slice number 1, for example, is going to give this kind of response, as we said, on the system, which is t for the response of the system, and the vertical axis here is going to be du, which means that part of the total response of the system. And for slice number 2, it is going to give us another, starting from here at the end of pulse number 2, then we're going to have like part of the total response for impulse number 2 or pulse number 2, and it is going to be along t, which is the time domain of the system itself, Okay, And then this technique, we call this technique in general, we call it the convolution. Okay, we call it convolution. This is known as convolution integral. Convolution integral. For those who interested in mathematics, you can find the meaning of convolution integral in mathematics class, which is a result or a general result that applies to any linear, take care of this word, linear dynamic system, which is, we are, in our case here, it is Duhamel's integral. Duhamel's integral. Okay, so just what I want you to remember, Will, that we are having different responses from the system, and we are going to add them up. We are going to add them up. Okay, every pulse is going to add up to the others until that we obtain the total response of the system, which is going to be U. And this U versus T is going to give us the total response, as you can see here. It is the summation and superposition of different and many pulses before. Okay. Remember, Duhamel's integral is used for linear. Again, I'm like placing emphasis upon this point because really it's an important issue. We're talking about linear system. You cannot use Duhamel's integral for non-linear system, or at least you need to modify it. Okay, so we are using linear single degree of freedom system only because it is based on the principle of superposition, as we're going to see, the principle of superposition. Okay, and based on that, we are going to find if our function, which is f of t, is a simple function, means that, as I said, like triangle, rectangle, or like pyramid, something like this, then the Duhamel's integral can be solved with a closed form solution. You are going to find the Duhamel's integral that we were talking about, it can be like solved with, or we can find closed form solution. The integral that you are fearing of is going to be changed to a closed form solution. But if not, the numerical solution methods should be used in this case. We are going to use our knowledge regarding numerical integration, numerical solution methods in order to solve the equation of motion. Okay. Now let's go to the next part, or the next hint about the impulse loading and the equation of motion. And I want you to remember that still we are talking about the effect of impulse on obtaining the total response of the system. This is what we are trying to have. This is what we are trying to have. So now we have a system. This system is having response u of t, but before we were talking about something that is very interesting here, because before we were talking about no initial conditions, right? If in the case that we are, if other initial conditions applies, for example, that u node does not equal to 0 and v node does not equal to 0, in this case the equation of motion that we have explained before is going to be changed. Okay, so it is not going to be only this part, it is going to be, we're going to add another part, which is going to be u node cosine omega t plus v node over omega sine omega t. And this is, we call it the free vibration part. The free vibration part. And the other part, which is the Duhamel integral that is usually, that already we have explained before. And this is what we call it the forced vibration part. Forced vibration part. Okay. If we look deeper to this equation, as usual, this is the free vibration part. If you remember that this is going to be like the transient part, and the forcing part is going to be the steady state part. Here you are going to find in the free vibration part, you're going to find the initial conditions are existent, u node and v node, right? In the forced vibration part, you're not going to find anything related to the initial conditions, right? in this part, which is the forced vibration, of course you're going to find the forcing function. However, in the free vibration part, you will not find anything related to the forced function. Okay. Note number 8, Duhamel's integral for damped system. Now we were talking about the undamped system. What if that we are having damped system? Okay. As we said before, the damped system or the damping in case of impulse loading is very small, right? But this is if we have individual impulse. But in general, if we're going to use Duhamel's integral for damped system, then we're going to find that inside the integration, we are going to use the decay term here, exponential function. So for the damped system, we are going to have, as you can see here, let me check this. So you are going to have omega d, which is the damping frequency of the system, and in the same time you are going to have the damping ratio here and the natural frequency of the system, and then the common time parameter, which is t minus tau. Sine omega d, again we are going to have the damping or the damped frequency of the system, okay, and then the remaining is d tau. Okay, so this is what we are going to have. This is what we are going to have in our case. Hint: damping effect on response to a single pulse excitation is usually not important. Very important concept. Remember that we were talking here u of t, it is for the whole system, okay? It is for the total response, okay? Under force that is going to be divided into different impulses. But if we are going to talk about the case where that one impulse only for single impulse excitation, impulse, impulse excitation. In this case, you are going to find that damping effect is not important. Damping effect is going to be neglected. Okay. The last thing is, in the case of earthquake loading, which means that complicated force that is being applied in the system, where the forcing function is complicated, okay, so it is not simple. Okay? Numerical methods need to be used for obtaining the solution. As we said many times, numerical methods very important for our case. And actually, if we have time, we can explain about numerical methods, but we have like different approaches for them. Chapter 5 in the textbook is talking about it in detail, so it is beyond the scope of this course. We are focusing on the understanding and rationale behind dynamic concepts. But numerical methods, it is well established, and there are many books and many courses talking about it. So anyway, just remember well that if we are going to talk about earthquake loading, then we are going to use numerical methods. Okay, because we are not going to have a simple form for our function. Okay, now let's go to the next. The effect of viscous damping on pulse excitation. This is an important thing that I think that we need to understand it well. Regarding this part, it is very important for us to know that how the damping is going to affect and why the damping that we were talking about is not going to affect the response in case of impulse loading. I'd like to read this part because it's very important also to understand it if you are going to, and I'm going to give like summary for what is written here. If the excitation is the single pulse, so this is the key here, that this is the key. If we're talking about single pulse, the effective damping on the maximum response, we're talking about the maximum response also, is usually not important unless the system is highly damped. I'm going to show to you a graph that is giving or like manifesting this the truth or this fact in this sentence, that you're going to find that the different for different damping system, that the maximum response will not be changed in in large values. This is in contrast to the results of chapter 3. Actually, for the case of harmonic motion, do you remember harmonic motion? Please, you can stop this video and recall the previous video that I was talking about the harmonic motion and what is the effect of harmonic motion and the damping on harmonic motion, whether in resonance, case of resonance or not. And if you remember, we were talking about that is, it is like the damping in case, or if we are going to talk about damping in case, effective damping on harmonic motion, if you remember, we were saying that for example, if we have damping ratio that is going to be changed from 1% to 10%, then the response or the deformation response factor RD is going to change from 50 to 5. Can you imagine this? It is really like amazing. So you are like, if we are going to have 1% damping ratio and going to be changed to 10%, then we're going to have RD, which is the deformation response factor, going to change from 50 to 5. So this is huge number, right? However, if you are going to talk about this on the pulse type excitation, I'm going to show to you what is going to happen for the pulse excitation. Okay, this is what is going to happen. This is the case of pulse. That is a relation between the horizontal axis here. It is going to be taken as T over Tn, and the vertical axis is going to be the dynamic response, which is U of t, over U static node, which is the maximum static response. This dashed line, it is considered to be the static response, okay, if the system is excited by half sine wave. And this dashed line, it is going to be traced by U static of t over U static node. As I said, do not be confused. U static means that the static force or the static response of the system with the changing of the time without considering any dynamic effect, over the maximum static response, which is going to be K, or as you know, this is going to be the relation between the system stiffness and the maximum amplitude of the force. So the solid line is giving to us the total response, dynamic response. As you can see here, the maximum response, total response, is going to be at point B, exactly at the end of the forcing excitation ends, exactly, and it is going to be a little bit higher than the static ones, okay, as you can see here. This is of course for a specific case where that Td over Tn equal to half, okay, which implies that omega equal to omega n, and we are talking about system for 10%. The variation of deformation with time, which is here, indicates that the maximum deformation point B is attained at the end of the forcing excitation. That's very true. Okay. Then we're going to draw this relation, which is giving and showing to us the energy dissipation, dissipated energy. This is a relation between U over U static node, the dynamic response over the maximum static response, and here it is a relation between the static force plus the dynamic force over P node, which is the maximum amplitude of the force. The dissipated energy is the shaded area that you can see here, the shaded area, because it's one pulse only, okay, this is one pulse. So you are not going to find that there is energy dissipated, because what makes the energy to be dissipated is the hysteresis, which is the the cycles while that the system is going back and forth, going back and forth, back and forth. So this is where the energy is dissipated. But other than that, it will not work for us. So if we have a single one pulse, there is no damping is going to be effective, and the response is not going to be sensitive to it. And this is what is written here. The total elastic plus damping force deformation diagram indicates that before the maximum response is reached, the energy dissipated in viscous damping is only the small shaded area, as we have seen here. This is the small shaded area that, as you can see it here. Okay, the energy dissipated in viscous damping is only the small shaded area multiplied by P node squared over K. P node, it is the amplitude of the force. K, it is the stiffness of the system. Thus, the influence of damping on maximum response is expected to be small. Okay, as I said, I want you to understand it physically, that one impulse will not make any difference, or damping is not going to take a major role here, because as you can see, the shaded area, it is only going to provide the damping energy. So as long as it is one pulse, there is no area, there is no big area, it's very small. But if we have like hundreds or thousands of pulses, for example, this means that we are going to increase this shaded area, and there would be damping for us, or damping forces, or damping or energy going to be damping energy would be developed. Okay, now I'm going to show to you, this is what we call it the shock spectra for half cycle sine pulse force for 5 damping values. Half cycle sine pulse, it is, as you can see here, this is like t, and this is f of, or tau, and f of tau, and here, as you can see, it is half cycle sine pulse. And we put it for different horizontal axis is td, which is the duration here. This is the duration, we call it td. Okay, the duration of the pulse itself. And Tn, it is the natural period of the structure. And in the vertical axis, it is Rd, the response modification factor or deformation response factor. It is U node, which is the maximum dynamic response over the maximum static response, as you know. And we have plotted it for different 5 damping values. Okay, for 5 damping values, starting from damping ratio equal to 0 and going to 1%, 10%, 20%, and 40%. If you're going to look to the common range that we are working on, we are working between 0.01, which is 1%, and 10%. This is what we are working commonly between, right? So you are going to find and realize that these two lines here, the blue lines, the difference here is very small. Okay, the difference is very small, not huge, not huge. So if we have like very large damping ratio, maybe yes, there is significant difference. Okay, but we are in this range between 10% to 1% to 10%, means that we are like 10% decrease or 12%. This is going to lead us to a conclusion that we can neglect damping, and we are going to avoid this headache in the solution of equation by the inclusion of damping, right? And this is what we are going to put it here. This prediction is confirmed by the shock spectrum, as you have seen, as we have seen it here. And the difference actually between these two responses, it is only 12%. It is written here, it is 12%. Can you imagine? Between 1% to 10% difference in damping, the maximum deformation is going to change only by 12%. Thus, and this is an important conclusion, a conservative but not overly conservative estimate of response of many practical structure with damping to pulse type excitation may be obtained by neglecting, that's very important, by neglecting damping and using the earlier results for undamped system. Yes, this is what we're going to gain at the end, that we are going to find that no need to include damping because we are going to be conservative. We're going to assume that our system is going to respond as if that it doesn't have damping, but really it has. Okay, so and if we are in the range of 12%, and I think that it will be less than that if we are having damping like between 1% to 5%, this decrease is going to be like around 6%. Okay, so this is very, very important and logic, and in the same time you are going to put yourself in the conservative side. Okay, so for half cycle sine pulse where TD equal to Tn over 2, the damping ratio, if it goes from 1% to 10%, the U node or the maximum dynamic response is going to decrease by 12% only. Okay, now let's go maybe to some examples on pulse forces, and then I'm going to end this video. I'm going to talk about the rectangle pulse force, so I'm going to talk about this type of pulse. Okay, this type, as you can see here, this type of loading. Okay, this is, we call it a type of rectangular loading. Okay, rectangular loading. Okay, and we are going to have like rectangular pulse forces, and I'm going to show here like half cycle sine pulse force. I'm going to show to you only the how it goes, how that we are going to expect the response of the system under different type of impulse loading. So I've chosen, you are going to find different types in the textbook, but I have chosen the rectangular type and the half sine wave type to see what is the response of the system for both. It's only indicative for you. Okay, for rectangular pulse forces, if you look here, you're going to find that this is the force that we have. This is the force that we have here. And as you can see, this is the equation of motion, mu double dot plus ku equal to p of t. This is the type of the function equal to p node, which is the maximum. If let's see, let's go here. This is p node here, the maximum force. And this is td. It will last for a period of td. Okay, so in this case, we are going to find that we are going to have two different parts. One part related to the forced vibration phase, and the second is going to be the free vibration phase. So this is the equation that is going to give us the response if we are talking about t less than or equal to td. Okay, and we are going to find, so this is for t less than or equal to td, and here this is for the case after the force is going to end. So we have here p node, this is p, and this is t, and this is the duration of the force or the pulse on the system. Our system, as you know, we are talking about like single degree of freedom system with stiffness k and the mass m, and p of t is applied in this direction. Okay, so you are going to find that we have two different types of phases: forced condition phase and free vibration phase. So if you go here, you're going to find, let's zoom on this. Sorry. So if you are going to look here, okay. So here, as you can see, first of all, the vertical is indication of the total response, which is u of t over the maximum static response, and the horizontal, as usual, it is going to be an important ratio, which is td, the duration of the pulse over the natural period of the system. And we are having different values, 4 different values. We have half, 1, 1.25, 1.5, 1.75, and 2. Then we're going to check what is the response of the system under every case. I do not want to go into the equations because equations are there for us, but I want you to feel these graphs and feel what is the difference between them. First of all, the dashed line, it gives us the static solution. It gives us the static solution. This is what the forcing excitation is going to provide, okay, which is rectangular here. You're going to find if our TD over Tn less than half, you are going like 1 over 8 and 1 over 4, you're going to find that the response of the system, which is denoted by the thick black line here, okay, the solid line, you're going to find that it builds up after the end of our system or the forced excitation part, right? Then the maximum is going to be here, for example. However, if our system is going to have Td over Tn equal to half, you're going to find that maximum is going to be here. This is the maximum for our case, right? At the end of the forcing excitation. And when we have 1, Td over Tn equal to 1, we're going to find something that is very interesting. The maximum is going to be almost halfway through, and at the end of the forcing excitation part, we're going to find that the response of the system is going to be, the system is going to stay still. Nothing here. Why? Because if you go to the equations, you're going to find in this case, look here, this is the free vibration phase. In this case, we have u of Td in the first term, and in the second term, it is u dot of Td, right? So at the end of this phase, you're going to find that these two values are 0, right? As if the initial velocity and the initial displacement at this point is going to be 0. This means the system is going to stay still. This is going to happen also when Td over Tn equal to 2. The same applies here, as you can see, because we are going to find that as if u, and because u of Td equal to u dot of Td, and both of them they equal to 0. They equal to 0. Okay. Okay. Now this is for this is the equation, and then you are going to find that, for example, the oscillation here, there was no oscillation for the free vibration, right? And here there was like almost 1 cycle, but here for Td over Tn, which is going to be larger than 1, you are going to find that there is oscillation, like sinusoidal, right? So this means that Td over Tn equal to 1 is considered to be a dividing line. Whether that the system is going to oscillate, whether around this 0, okay, or not. And in the same time, the maximum also is important. You are going to find, for example, for the case of Td over Tn equal to 1.75, you're going to find like two maxima here. Similar for Td over Tn equal to 2 maxima. And then you are going to find the system is oscillating after that, right? So that's an important issue. For the case of Td over Tn less than half, which is the first, which is 1/8 and 1/4, there is an interesting observation here, which is if Td is shorter than Tn over 2, no peak will develop during the forced vibration phase, and the response simply builds up from 0 to u of Td. That's very right. Look here, there is no maxima here at all. But whenever that Td over Tn goes beyond 1, you are going to find the maxima is going to develop here and here and here, for example, right? That's the main important notes about this this one. There is an interesting observation as well, which is after even Td over Tn goes beyond 1 and maybe reaches 2, the response of the system does not follow exactly the force excitation pattern, right? This is an important issue because in the next half sine curve, we are going to find that the system is going to follow the force excitation. Okay, the force excitation. Let's see. Okay, I want to highlight the important things here. I think that I have mentioned everything here. So let's go to the next part, which is half cycle sine pulse. Okay, in this case, the next pulse that we are going to consider is the half cycle of sinusoidal function. Okay, that is, you can see it here. This is the system, or this is the pulse, half cycle sine pulse wave that we are having here. The same, it's Km for our system, and P of t is applied, and this is the direction of the loading and the response. P versus t, and the duration of this half cycle sine wave is Td, and this is the peak or the amplitude of the force being applied, which is P naught. Okay, then you're going to find that these are here the cases for us. Here are the cases for us. As usual, you're going to find that for Td over Tn, like less than half, like 1/8 and 1/4, still the force or the response of the system is building up outside of the forcing excitation part. However, if you are going to near to half or 1, you're going to find that the response of the system is going to follow the dashed line to some extent. If we go and reach like 2 or 3, you're going to find that almost we are the same trend with the excitation force. This is one major difference between the sine, half cycle sine, and the previous one. What is the reason for this? Because in the previous case, the force that is being applied, it is like abrupt force that is not gradual. Directly we trigger the system with P naught, the amplitude, from t equal to 0 till t equal to Td. However, in the case of the half sine case, we are having gradual change of the force, that is at t equal to 0, P naught was 0, and then at Td over 2, the value of the force reached its peak and then goes back to 0 at t equal to 2d. This kind of gradual change of the force is reflected on the response of the system. The more that we are going to increase the ratio between Td over Tn, as you can see here, the more that the pattern is going to be followed for the forced excitation. And one interesting system, or an interesting also like observation as before, that here the response is going to be of the system is going to be outside. Here it is going to be like outside, as you can see. Okay, builds up. It goes here in this direction and builds up here. However, if Td over Tn, it is going to be going to 1 and 2 and 3 and 4 and so on, then you are going to find that you are, like as you can see here, you're going to find that the peak is inside the pulse duration. As we have mentioned before, the peak is going to be inside the pulse duration for our case. Okay. Here the response tends to follow the static response because the force applied gradually, not like the rectangular case, and this is very true. Okay, I think that this is maybe brings us to the end of this video. Thank you very much for listening to me. I know that it's a long video, but anyway, it is very important to stop the video at any time and try to understand what I have explained. I try to simplify the concept of pulse loading and how we can obtain the response of our system using pulse loading. Anyway, this is the video of today. Thank you very much and see you next video.